Good morning, everybody. So today we're going to learn about characteristics of sound waves. Last year, you learned about light, how it reflects, how it refracts. This year, we were going to learn about sound. Alright, so our surroundings are filled with a variety of sounds. Can you hear this? See? Sound. Sound is a form of energy, caused by vibration. For example, the musical instrument in photograph 10.1 produced sound through vibration. Okay, so here's what you can do. Try touching your throat and then talk. Can you feel the vibrations on your throat? So basically, sound is produced by vibrations. So in this case, let's say the woman playing a flute. The sound is actually caused when the air has to travel through all of this. The air has to travel through all of this, and it goes through different obstacles inside here to make noise. Why? Because as the air travels, it has to move very rapidly, and hence causing the vibration. Now, for our things like guitar, you notice when you move the guitar or when you pluck the string, especially the thicker ones, it's easy to see in the thicker ones down here, you will see that the string will actually make a wavy shape when you pull it, alright? It looks wavy right now, but in reality it's actually moving from side to side or vibrating very fast. Okay? So in that vibration will actually produce sound. We'll explain how it produces sound that you can hear in a bit. And then when over here, let's say the fellow playing this drum. So every time he hits this thing, the diaphragm of this drum will actually vibrate. Alright? It'll vibrate in different kind of frequency depending on the size of the diaphragm. And then that will also produce sound. Now, let's go through some experiments that will actually show you the characteristics of sound waves. So have you ever seen this experiment? I want you guys to watch a video later on, okay? Because you cannot do this at home, unfortunately. So we have here a bell or an alarm clock, and we put it inside the bell jar. So when you turn the alarm clock on, you can actually hear the sound, right? Because the sound will travel outwards, right? However, if we were to connect a vacuum pump inside here and take out all of the air inside this bell jar, what will happen? Alright, I want you to think about it. Or better yet, pause the video and go to this video, which I'm going to put in the link in this description, right, and watch and see what happens. Okay, if you guys have already watched the video, so what happens when the air is pumped out? So initially you can hear the bell ring, right? And then eventually you'll hear it go softer and softer and softer. So what happens here actually is, let's just pretend that inside here we have this blue thing. Let's pretend these are air molecule, right? So when there are a lot of air molecules, you can actually hear the alarm clock ringing. So as the vacuum is actually sucking the air molecules out, you see, the less air molecules there are, the softer the volume. And then eventually, when there are no more air molecules inside the jar, you cannot hear a single thing. So this shows you what? This will actually show you that sound cannot travel in a vacuum, or sound needs a medium to propagate. Right, the next experiment is, we can see, it's propagating at different speeds in medium. Right, so in this experiment, what you can do is get a container or a plastic container or cup with an alarm clock. Now prepare 3 plastic containers that are filled with air, water, and flour respectively. Okay, place the empty plastic container filled with air tightly onto the table and place your ear to the container, like here. Now ask your friend to, or ask your siblings to activate the alarm clock and at the end of the table and try to listen to the sound produced. Okay, repeat steps 2 and 3 using the containers filled with water and flour, and then compare the loudness produced. Okay, so what you'll find that sound, instead of traveling to your ears through the air, it can actually travel through the book, through whatever medium you put in here, and to your ears. So using different materials such as air, water, and flour, you will see that the sound actually can travel through. Here's an interesting thing. If you don't believe that sound can travel through solids, I want you to just put your ear on the wall. Put your ear on any wall, okay? Or even better, you can put your ear on the table. And I want you to knock. I want you actually to knock to either the wall or the table, whichever your ear is on, like from an arm's length away. You can actually hear it. Can you? Alright, so the next one. Sound. Oh, but before that, in this experiment, you'll actually find that sound can travel through different mediums, such as solid, liquid, and gas. Remember, no vacuum, but it can travel through different mediums. Alright, now for the last one. Sound can be reflected and absorbed. So how can we test this out? Okay, basically what we need is a table, cardboard tube, analog stopwatch, or if you don't have one, you can also use a small alarm clock with not a digital one, an analog one, plasticine, wooden plank, metal sheet, softwood, and towel. So set the apparatus up as shown like this. Okay, so now move tube Q until you can hear the cardboard ticking. Without moving the P and Q, replace the wooden plank with metal sheet. Alright, and then after that, a towel. And then now you should compare what will happen. So the whole idea is we want to use a metal sheet or something hard, okay? And then after that, we also want you to try to use a towel, which is something soft. Okay, so when you set up this experiment, you will hear that the ticking noise will travel, bounce off this wood, all right, and then will come and go to your ear. So when they ask you to put a metal sheet in here, let's say this is a metal sheet, all right, they want you to hear whether you can, they want you to check to see whether you can actually hear the sound waves. And since that the metal sheet is quite hard, you would be able to hear the sound. Now, what happens if you replace that with a towel? Right, what you'll find out is the sound waves will actually go here, and after that it will basically be absorbed by the soft towel, and you would be unable to actually hear the analog stopwatch. All right, why do we need a softwood in between here, by the way? Okay, if you're actually looking at this from the top point of view like this, the diagram should look something like this, where you have a stopwatch here, and then over here you would have this thing would be either the metal sheet or towel, right? So since we have a divider here, the sound will not go to your ear directly, okay, because it's being blocked by this divider. Okay, now theoretically the sound should go over here, all right, and bounce off this surface and reach your ear. Okay, so you replace it with a towel. What happened is the towel will actually absorb a lot of the sound wave, if not all, and you will not be able to hear anything. Okay, so which one would be a good absorber of sound? It would be the metal sheet. No, it will not be the metal sheet. Absorber, it absorbs. It will be the towel. A good reflector would be the metal sheet. Right? What are the properties of a towel? It is soft. Metal, it is hard. So what we can say from this is, again, soft objects absorbs sounds, whereas let's just write it here. I'll write it here. Whereas hard objects reflects sounds. Okay, now let's talk about the transfer of sound. Sound requires a medium to propagate. Sound can propagate through solid, liquid, or gas, but not vacuum. Remember, okay? No vacuum. For example, over here, right? When the bell is rung, the metal surface of the bell will vibrate. Okay, this thing vibrates. Air molecules near the surface will also vibrate and collide with the air molecules nearby. So the air molecules over here will vibrate, and then it will also collide with other air molecules nearby. Alright? This vibration is transferred to one molecule to another molecule beside it in the form of waves. In this way, the bell produces sound that we can hear by the ear of the listener. So basically, when the bell vibrates, right, it will also vibrate the air nearby, and this air will vibrate the molecules nearby it, and that will also vibrate the molecules beside it, and so on. So basically, you have a continuation of vibration of air molecules next to each other, and that will eventually travel outwards or away from the source and be detected by our ears. Right? So let's talk about how the speeds of some of the some of the medium that we'll study. Alright, for speed, and let's talk about gas first, alright? We'll talk about gas first. Sound waves propagate very slowly in gas because the arrangement of gas and particles are very far apart from each other, causing a delay in transfer of vibration. So remember example up here, alright? So when the air particles or molecules vibrate, okay, they have to knock another molecule to actually transfer the sound energy, right? But we know that in a gas, the molecules are far apart. So hence, it will take a little bit of time for them to find the next molecule to hit, and this one will find another one to hit, and this one will find another one to hit. It will take a little bit of time. Therefore, sound waves propagate in air very slowly. Let's look at liquids. So the loose arrangement of particles in liquids causes the sound vibrations to be transferred less rapidly compared to solids. Okay, so from gases we know that it's very slow. So over here, when we look at liquids, it's a little bit faster, right? Why? Because it's a shorter time to find the next particle. Okay, that's how sound will travel. Okay, so we know that this one is slowest for gas. This one is also slow, but not as slow as gas. Or let's just say medium. Now let's talk about solids, alright? So sound is transferred very rapidly in solids. When the particle at one end of the solid starts to vibrate, the vibration causes the nearby particles to also vibrate as the particles of the solids are arranged very closely together. Okay, see now, this particle here? See how close is it to this particle, and this particle, and this particle. So the jump between all of these particles is very small compared to your big gap in gases and also liquids. Therefore, sound will travel a lot faster. Okay, it'll travel a lot faster in solids. So if we are going to group them together, we have sound in solids will be faster than liquids, liquids will be then gas, faster than gas, and gas is slowest. Okay, now we did talk about reflection and absorption of sound in the experiment that we did just now. Yeah. So keynote, the thing to note is for hard, let me use different color for this. For hard and smooth surface, they are very good sound reflectors. Meaning, alright, hard, smooth. Reflect sounds, okay? And then for soft and rough objects, they are good at absorbing sounds, right? This is why if you wear boots, okay, very hard boots, and then you walk and do marching, okay, you can hear the sound very loud, right? But if you wear like really soft rubber shoes and try to march, it's not very loud. Okay, the same thing. If you shout at a wall, a hard wall, you'll hear the echo eventually if the room is big enough. But if you shout at, like, let's say a curtain, you can't really hear the echo. Okay, So remember, for this lesson, okay, sound travels fastest in solids, okay, and it travels slowest in gas. It travels slightly less rapidly in liquids. So the order is solid, liquid, and gas. Right? Another key thing is it does not travel in vacuum. No vacuum. Okay? And lastly, what you'll need to know is hard surfaces or smooth surfaces will reflect sound. So they're good at reflecting sound, bad at absorbing sound. And then soft or rough objects, soft or rough surfaces will be good at absorbing sound and bad at reflecting sound. Right? Okay, that's all for today. Thank you.